0 over 0, infinity over infinity, and awesome. Very good. Well done. Now I would like to look at this limit. As x approaches 0, from 1 plus 1 over x raised to x. Okay. When we're asked to determine a limit, the first thing we do is plug it in. Okay. So when x approaches 0, I always have to look at the inner function first, right? This is the outer, this is the inner. Okay, when x approaches 0, where does this go?
0.
How much is 0 plus 1?
1.
Good. So,
Don't forget the limit operator.
no, I just wanted to talk about something. That was good.
1 over 0 not
No.
a thing.
I messed up. It's infinity here. I'm sorry.
Oh.
That's why when I got to 1 to 0, that's not an indeterminate case. And I said, oh no, I did something, and that's what I did. Okay, let's start from the beginning. We have a limit with a 0 too in a minute. You'll see. So limit as x approaches infinity, this approaches 0 plus 1 is,
1.
and this approaches. Okay, this is, see, when I got to, I was supposed to write 1 raised to 0. I said, no, this is not indeterminate. So this is another indeterminate case.
Why?
It's on the list of 7.
Wouldn't it just be 1?
Very good question. You will see it's not going to be 1.
Okay.
Yes, it's not going to be 1 at all. Okay, ready? So I have this limit. I know it's 1 to infinity. And my only chance is L'Hopital's rule. But L'Hopital's rule is not applicable in a case. First of all, this is not a ratio. Oh, I can make it into somewhat, but it has a power. It's not a ratio. So I cannot apply L'Hopital's rule. For one reason, not a ratio. And for second reason is L'Hopital's rule requires
0, 0, 0.
or infinity over infinity. Okay, but I just learned something a minute ago.
What did you learn?
I learned that I can denote this function by y, and I can change it from a function raised to a function, applying.
Natural log.
So then natural log y is, very good, awesome, perfect. Now you should say, are you okay? Okay. Now you should say this. Okay. You were asked to find this limit. You took the function out of the limit. You denoted it by y. You apply natural log to both sides. And now, instead of finding the limit of the function, you are going to apply the limit to both sides. And you can say, but you're losing track of limit of the function. Not at all. You'll see it in a minute. So I'm going to apply the limit to both sides. This is an equation. This is an equation. Make sure that you don't, right? So this is limit as x approaches infinity from natural log y. And you could say, who cares? This is not what you are asked to do. You're asked to find the limit of the function. You're not asked to find the limit of the natural log of a function, of the function itself. Stay with me in a minute. You'll understand what happens here. So the left-hand side is limit as x approaches infinity from, and I hope you allow me to, we can keep it as is. We don't have to. Natural log 1 plus 1 over x. So I'm going into a roundabout way. I'm having difficulties finding limit whenever I have an indeterminate case like this. So I have to manipulate the the function somehow. So I denote it by y. I apply natural log to both sides. So now I'm trying to find the limit of this. But the limit of this, of natural log, is the limit of this. Now I'm going back in and say, okay, let me see what type of limit is this. Now, where does this go? Where does this go? Where does this go? How much is natural log 1? 0. And what is this? Another indeterminate case. It's on the list. However, this indeterminate case is friendlier. This one, no, not at all. But I managed to, applying the natural log, I managed to change this into this, which is more human. What do you think I'm going to hope now that I can do? Change this into, or 0 over 0, or, because,
No.
exactly. Exactly. Okay, so then I'm trying to change this into either infinity over infinity or 0 over 0 somehow. Here's how I'm going to do it. Do not move natural log anywhere, because natural log is going to be a big problem if you want to move it to the denominator. It will have a negative power, very complicated. But I'm going to rewrite this expression in the following way. Obviously, I need a fraction. If I don't have a fraction, I cannot use L'Hopital's rule. So what did just happen? I hope you agree that the numerator has to be multiplied by x over 1 to get this. So instead of having x next to log, I inverted and I put in the denominator. So this expression is identical with this one. Now I check again. Exactly. So the most difficult part was to change this one into this one. Once I have this, it's much easier by a simple algebraic manipulation. Since it is 0 over 0, now I'm ready to use L'Hopital's rule. So limit xx approaches infinity. That's why I said, please commit to memory the derivative of the denominator, which is perfect. Now, yes, please.
Sorry, I missed how we got to natural log of 1 over x.
So how we got from here, here?
Yeah.
Okay. So I saw an x in front, and I said, what if I put 1 over x in the denominator? So the numerator divided by the denominator means that I have to multiply it by x. I needed to change that expression into I just changed it into the denominator, into 1 over x in the denominator, because I need this to be a ratio. Why do I need to be a ratio? Because I need 0 over 0 or infinity over infinity. Otherwise, my hands are tied. So now the derivative of the numerator, please.
1 over 1 plus 4x.
Times. Exactly. But don't forget to put parentheses. And look what happens next. 1, 1. I was able to remove the negative 1 over x squared from the top with the negative 1 over x squared from the bottom. And now please plug it in and tell me what you get.
1.
Awesome.
1.
Indeed. Because when x approaches infinity, this approaches 0. 1 plus 0 is 1. 1 over 1 is 1. So now, here's what I'm going to do next. I'm going to look at the very beginning, not at that one here. I'm going to look at the very beginning and the last. I'm going to copy just this piece and this piece, because the limit of this is 1. So, limit of natural log y when x approaches infinity is 1. There was a very, very important theorem a while back that I said it will come into play. Just keep in mind that it exists. We used it several times. I didn't tell you we used it. So here's one application. We said, what about the limit of the square root of f as x approaches a? This is the same with the square root of the limit of f as x approaches a. This was one of the properties, the 11 properties of the limits from chapter 2. So what really happened here? This is an operator, the limit operator. This is another operator, which is the square root operator. What did we do from here? We swapped them. The same thing here. This is an operator, and this is another operator. Under conditions of continuity, of course, I am allowed to take this outside exactly how I took the square root outside of the limit. So then this becomes natural log of the limit of y as x approaches infinity is 1. From the very beginning, what are we after? We are after limit of y, correct? So I am after this. What can this be? What should it be so that its natural log is 1? And there is only one answer. This must be e. So therefore the limit as x approaches infinity from 1 plus 1 over x raised to x is not 1, but how much? It is e. We can do the other one. Let's do the other one. Yeah, it's very similar.
Were we still on the same?
Yes. Yes, we were on the same page. We were doing
Might be easier
this.
to go over what we've already gone over.
You want to go over this again?
Well, not over, like where E came from.
We can. What if we do the other one and then we come back? Okay, let's do this one. Let's do this one. Got it. Okay, so we want to talk about it or we want to write it from scratch?
We can talk about it.
Okay,
Yeah.
so
I can't write.
we were asked to find the limit of this function.
Yes.
So every time I'm asked to find the limit of a function, I have to plug it in for many reasons, especially to see if there is an indeterminate case. If it's not an indeterminate case, it may be just 5 and I'm done. But I have to plug it in. So when I plug in infinity here, we know that this approaches 0. And we know that 0 plus 1 is 1. And when x approaches infinity, this approaches infinity. So this is the indeterminate case. This is the most difficult one. Okay? 0 times infinity is much easier to handle. Infinity minus infinity is easier to handle. 0 over 0, infinity over infinity. This is one of the most difficult, I would say. So I have to do something about it. So we took this function aside. We realized that this is a function raised to another function. So that should trigger our memory a little bit. Because a function, and you can say, but that's a derivative and you're talking about the limit. Correct. But it's a function raised to a function. And my target is to get a limit of a ratio so I can apply L'Hopital's rule. So for that reason, function raised to a function, we thought immediately of natural log. So we denoted this by y, and we apply natural log to both sides. We moved x in front with a property, and then I said, okay, let me find the limit of this and see what I'm getting. And then I'll see what the next step would be. So we applied natural log, we applied limit, and I leave this alone because this I can work on. Okay, so it's limit of x times natural log. I check it, not yet. Not check, because when x approaches infinity, this is infinity, and this is 0. So infinity times 0 is a different indeterminate case. But right now, I can get 0 over 0 or infinity over infinity. I don't want to move natural log the denominator because it becomes with a negative exponent. And I don't want to have to differentiate natural log raised to -1. But if I keep natural log and I flip x into 1 over x, then I change this product into a ratio. Is it clear how I can get back from here here? Okay, so now I plug in again. The numerator approaches 0, the denominator approaches 0. I'm in business, it's a fraction, it's 0 over 0. I can apply L'Hopital's rule. When I differentiate the top, it's natural log of a function, 1 over the function times the function prime. So when we differentiate this, 1 prime is 0, and this prime is that -1 over x squared. L'Hopital's rule says you do not apply the quotient rule, right? If it's a fraction and it's 0 over 0, infinity over infinity, you differentiate the top by itself and differentiate the bottom by itself. We never ever do that in real life, other than a limit, inside a limit. Okay. So we realize
The hospital's rule is only applied to limits.
only to limits, only, don't forget what you want to say, Sid. Only to limits,
When
only
infinity-
to ratios, and only if the indeterminate case is
Yep.
0 over 0 or infinity over infinity. See that?
So would you also, so let's say you didn't get the 0 over 0.
Then I'm in big trouble.
Could you still, could you still use the quotient rule instead of Hospital's rule?
We never use the quotient rule for differentiation inside the limit ever. Very good question. So the derivative of that is this. The derivative of this is this. It turns out that these two go away. Same quantity top and bottom. I say x approaches 0. This is 0. 1 over 1 plus 0 is 1.
Yep.
At this point, I copy the beginning and I copy the end. So here's what I have. I will not ask you to reproduce this. So you don't have to worry about that. We can look at other problems that are important later. But I'm not going to ask you to reproduce this proof. I want you to see the idea. Okay? Number 2, I want you to understand where this E is coming from. This is Euler's number. That's how he determined it. Okay? That 2.71, A28, and so on and so forth. That's how he determined it. And there is another way, of course. Okay, so we copied the beginning and the end. And then I stopped here because I wanted to remind you of something. A long time ago, when we studied limits and limit laws, we said the limit of a square root of f is the square root of the limit of f. And what happened here? I swapped these two operators. The square root, which is an operator, the limit, which is another operator, one went in front of the other, or one above the other, right? So I was able to swap this. The same thing here. The square root is like natural log. The limit is like limit. So I'm allowed to swap these two, assuming natural log is continuous. Otherwise, I can't do this. But yes, it is. So then from here, we wrote this. Then we copied 1. And now the question is, natural log of a certain quantity is 1. What can the quantity be? There is only one number whose natural log is 1. And that is E. So in a roundabout way, I was able to determine this is the limit of y. Limit of y is E.
So it wouldn't have. So is it on? Does it have to be 1 plus 1 over x?
There is a second possibility, which is limit as x approaches 0 from 1 plus x raised to 1 over x. I don't want to spoil it, but what do you think the answer would be?
I'm going to say e. But it couldn't be like say x squared plus 3 to
Very,
the x power
very good
equals
question.
1.
Very good question. Let me look at those problems and see where they are. It's a very good question. I think they're in chapter 4. Very good. Let me see. I don't want to waste your time if it takes more than 30 seconds. And I think that they're in section 4. Very good question. We can work on a problem like that. Yes, here they are. Limit of a function raised to a function.
Yeah.
It's the exact same procedure, but this is in chapter 4, and it's in the section entitled.
The terminator.
I can't wait till then. I cannot just give you say this is E and I'm done. I can't. So I had to present L'Hopital's way ahead of that. So if you want, we can work on a problem like that if you're curious, or we can do this, or we can do something else. You choose. Say it again. You want to do this one? Very good. Perfect. So let's say we don't know what it is, and we're asked to find this limit. I plug it in. Okay. In this particular case, 1 over x when x approaches 0, we are going to consider that this is a positive side. It doesn't matter if it's negative. It's still in the terminal case, but let's say it comes from the right. So this is again 1 to infinity. The same thing we started with a few minutes ago. What will be the next step? Well, I have to denote 1 plus x raised to 1 over x. It's a function raised to a function. My only chance is to apply natural log. There is nothing else. So natural log y equals 1 over x times natural log 1 plus x.
Is that the limit of as x approaches 0?
Well, because see, 1 over 0, right? 1 over x looks like this going to 0 from your right, and it looks like this as you go 0 from the left.
Oh, okay.
So let's just focus on one side.
So
The limit from either side of 1 over x is dne.
would this also work if it was 1 to negative?
Yes.
Same thing?
Yeah. Okay, so I have natural log y, which is this. Lucky me, this time, this is already a what? It's already a ratio, so I don't have to manipulate anything. And now I'm going to apply the limit as x approaches 0 to natural log y, which is the same with the limit as x approaches 0 from this ratio. And this is pretty nice because it's done. The limit of the top goes to so when x approaches 0, the top is
Natural log of 1.
0. Perfect. And when x approaches 0, the bottom is perfect. So then I have a limit as x approaches 0. Now I'm ready to differentiate. The top is 1 over 1 plus x times the inner function prime, which is, and the denominator is,
1.
and the answer is
1.
good. I write the top, the first and the last. Limit as x approaches 0 from natural log y is 1. I'm allowed to swap the two operators under certain conditions of continuity. So this is natural log of limit of y as x approaches 0 is 1. And now I'm asking myself, what can that be? And there is only one number whose log is 1. So it must be e, so I can go back and say e.
Once the infinity power is always
You are saying when the power is infinity, but it depends. Let's look, since you mentioned. Okay, let's choose a problem from here. Since we are here, why not? Okay, let's choose one. 59 through 66.
I think you know which one we do.
I have no idea what you would like.
The blurriest one.
Oh, nobody can read?
It's all blurry.
Oh no, I'm sorry.
That's because you were holding it up if you let it.
Yeah.
Oh, I'm sorry. Okay, so let's look. On page 308. So this is in chapter 4. I just
Yeah, not do that.
no, we're not. Just in case you wanted to see another example like this. Okay, so we can wait to chapter 4. There is no rush. Okay, so back.
Do you remember my question then?
Yes.
Okay.
Yes. Your question was, in all these situations, do I get E?
Yes, when it equals 1.
Right. So if it equals 1, it would be E. But if it's, for example, 8.
That's not what I'm asking.
Oh.
So.
So if you
Yeah, the net, it's the.
if you do
Go up, well, if you go a
the
little bit.
natural log of y equals
So what I'm saying
Yeah.
is that if you get, instead of 1, if this is 8.
It's not.
No. I'm talking about. So, let's say this wasn't one. This wasn't the power. It was x squared plus something in there, and then to x right there.
I have to look at the problem, and the indeterminate case has to be 1 to infinity. So whatever you give me, if the indeterminate case is not 1 to infinity, most probably we're not going to get to a power of E. So make up an example and we can work on it.
So if you're doing a limit problem
Yes,
and you plug it in and you get 1 to the infinity,
yes. You are going to try. So I don't know. I have to look at the problem. You may get something with E or not. It depends. But one thing is for certain. If I get the indeterminate case 1 to infinity, I'm going to try everything in my power to change it into 0 over 0 or infinity over infinity.
so 1 to the infinity power could be anything.
Yes. Like 0 times 0 times infinity. The same thing, right? So just don't forget what you want to say. A minute ago, we had this. So we changed 1 to infinity into infinity times 0, which turned out to be 1. So that's why they're called indeterminate. No one knows what you can come up with. That's why they're indeterminate. Yes?
Do we have to write that it's E?
In here, there is no other number. Natural log E is 1.
Well, yeah, but I mean, can we leave it as 1? Or do we have to write
But this is just an equation that allows me to solve this. This is gone. I'm done. So this is just an equation saying natural log of what you are looking for is 1. Then what you are looking for must be E. Is that clear? So if I tell you,
But is the answer not 1?
no,
It's
the
E.
answer is E. This is what we are calculating. We are calculating the limit of y. And in a roundabout way, we determined that natural log of that is 1. Therefore, this must be E. There is no other way. And this is what we're after. We're after the inside, not the natural log. This was a tool that we used to get to where we're going. But this means nothing. That's not the question. The question is limit of the function, which is here. So, if I manage to find this, I found the answer. And from this equation, I can only come up with one answer. And the answer is, what could this limit be? So that natural log of this number is 1. The answer is E. That's why this is E. And that was the starting point.
So what do we do with the power?
Say it again.
What do we do in cases where it comes up?
Very good.
8?
That's a very good question. So what if I have limit, I'm going to just write this already, natural log of the limit of y as x approaches 0, and I get 8. Good. So what could this be so that natural log of this is 8? E to the 8. Only e to the 8. Natural log of e to the 8 would be 8.
So it does not matter what is in the parentheses as long as it's natural log to that
Yes,
equals 1.
equals whatever.
But,
And
yeah,
then
okay.
I'm able to determine what I'm looking for. So we change this into 8. So now this is still our limit that we want to determine. What can this be? It has to be e to the 8 because natural log of e to the 8.
I think that's basically what I'm saying. Like
Okay.
the equation in the parentheses next to natural log, as long as it
Is
equals
what we're
1,
looking for. Doesn't have to be 1. It can be anything.
Well, exactly, but then it's
Yes.
but it's going to be e to the whatever that
Whatever.
is.
Exactly.
Okay.
Yeah.
Now
So that this will be then limit as x approaches 0 from y.
okay, perfect.
But the moral of the
Story.
story right here is remember 1 to infinity, how to handle it, and remember how to handle infinity times 0. And both of them, I'm hoping that I can get to 0 over 0 or infinity over infinity. Otherwise, the situation is way more difficult. Okay, so we're back. Other questions? Anything else from 3.6? Anything else? For example, you can try at home. Okay, let me see if it's blurry. You can try at home. Show that the limit when n approaches infinity from 1 plus x over n raised to the nth power is e to the x. And it has to be x greater than 0. You can try that. It's 56. See what you get. Okay, so let's look at some applications of differentiation rules. So this is 3.7, applications. Let's start with the problem. Let's take problem 7. We're going to apply what we learned. And really nothing sophisticated, really, not what we just discussed. Nothing sophisticated. Okay, the height in meters of a projectile shot vertically upward from a point 2 meters above ground level with an initial velocity of such and such. We are given the function h of t, which is 2 plus 24.5 t minus 4.9 t squared after t seconds. So the height, which is this, is measured in meters, and t is measured in seconds. First question, first application, something that you would definitely love to have on the test, and you will. Find the velocity after 2 seconds and after 4 seconds.
That's just h prime at 2.
Exactly. If I don't have the function, I cannot plug in. Very good. So v of t is h prime of t. First, we have to determine the function and then plug it in. So what do we get? Obviously, this is a quadratic function, very, I would say, easy to handle, correct? So 24.5 minus 9.8t. So this is the function that represents the velocity, which is the rate of change of the distance with respect to time at any point where the function is where the function is differentiable. But this function is a polynomial function, is always continuous and differentiable. Okay, so now they are asking us to find v of 2 and v of 4. If you can give me those numbers, then we'll continue. when does the projectile reach its maximum height? And no, I don't want to use algebra on this. Do we have the numbers?
4.9,
Was it
4.9
measurement unit?
meters.
Very good. No, this is not the acceleration yet.
Oh, sorry,
And the other one?
negative 14.7.
Meters per second. The negative and the positive, they only give us the direction. In part B, one more time, we're asked, when does the projectile reach its maximum height? Exactly. Exactly. So maximum height when v of t is 0 or h prime of t is 0. And this is all what chapter 4 is all about. This is what it is about. Okay, so v of t, it's 24.5 minus 9.8 t equals 0. Or negative 9.8 t equals negative 24.5, or t equals how much?
24.5
Which is how much? 2.5 seconds. Now, we did not need calculus for this. How do we determine the max or a min of a quadratic function? First of all, does it have a max? Why? The leading coefficient is negative, definitely. How do I determine the max? Negative b over 2a. So negative b over 2a should give us what? Let's check. So negative b over 2a, negative. B is 24.5. 2 times a is negative 9.8. And the answer is 2.5 seconds. So we didn't need for the quadratic function, we did not need calculus. For other functions, we do. For other functions, we do. Part C. What is the maximum height? How do I determine the maximum height?
You play 2.5.
Of course, it's the same thing from the quadratic function. So h of 2.5 is 2 plus 24.5 times 2.5 minus 4.9 times 2.5 squared. When you're ready, please tell me what it is. And the measurement unit. Then we're asked to find when it hits the ground. How much?
Oh, sorry.
So the next question is, when does it hit the ground? Do we have this number?
32.625 meters per second.
32.6?
Yeah.
Okay, so this is meters. Is that okay? Did we get the same thing?
Yeah.
Can you, okay, perfect. When does it hit the ground? What do I have to determine? When, yes, I have to determine x or t, but what do I have to write in order to solve and get? Very good. Age of t is 0, which means the height is 0 when the projectile hits the ground. So then we have, I'm going to write in descending order, negative 4.9 t squared plus 24.5 t plus 2 equals 0. My only chance is to use the quadratic formula, but I refuse as long as it has a negative leading coefficient. So 4.9 t squared minus 24.5 t minus 2 equals 0. Negative b plus or minus the square root of b squared minus 4ac. I have another minus plus. 4 times 2 is 8 times 4.9 over 2 times this, which is 9.8. I know you know, but I would like to show you how to put in the graphing calculator. So parentheses are on the top, and I have 24.5 plus the square root in that's not what I meant. Why is it doing this? Never mind. So 24.5 plus the square root in parentheses. You know me, it may work without, but I can't. Old school. Okay, plus 8 times 4.9. Close the parenthesis inside, close the parenthesis outside for the numerator, and divide by 9.8. So this is roughly 5.08. So t approximately 5.08 or 5.1 seconds. Now I want to determine the other one with second and entry. And I overwrite, yes, exactly. Into minus. And the answer is unacceptable because it's a negative number. So when we throw the projectile in the air, in 5.1, roughly 5.1 seconds, it will hit the ground. The other one makes no sense. Part E. With what velocity does it hit the ground? So V of 5.08. So what was V again? It was 24.5, right? And minus 9.8, correct? Yeah, I have it. So this is 24.5 minus 9.8 multiplied by 5.08. So when you give me this answer, I hope you agree that this is more human than the natural log, the limit of a natural log, in which the answer is E. Right? Okay. I would like to look at 31 on 236. So this will be in meters per second on 236. This section is not done. We still have other applications here to look at, but I'd like to, I know I have 4 minutes, so I'll do what I can in 4 minutes. If not, I'll stop. Say it again.
Negative 25.28.
Oh. 25 you said?
Yeah.
25.28. Okay. The reason why it's negative is because we throw it with a positive height, with a positive direction of the speed, and then it's a negative direction of the speed. Okay, the cost in dollars of producing X yards of a certain fabric is C of X 1200 plus 12X minus 0.1 X squared and plus point, I see 3 zeros, correct me if I'm wrong, X to the third. Okay. First question is, find the marginal cost function. What is the marginal cost function? The rate of change of cost with respect to X is measured in yards. So the rate of change of cost with respect to the number of yards we produce, right? That's the marginal cost. So part A will be C prime. The rate of change at any point. And obviously we get 12. We get minus 0.2x and plus 0.0015x cubed squared. So let me check. So I have 15, right. This is the marginal cost function. Marginal cost function. Part B, and then I'll stop. find C prime of 200 and find it and explain its meaning. What does it predict? Exactly. So this will be 12 minus 0.2 times 200 plus 0.0015 200 squared. And when you want to give me this number. And then part C is very interesting. It's actually the most interesting of all. But I guess I will not hold you over. I have almost 8:45. Oh, we finish at 55. Ah! Some classes finish at 8:55, others at 8:30, and it's okay, I have time. Ah. Awesome. So what is the number? How much? 32. Measurement unit. This is the rate of change. So it's dollars per yard. Very good. Part C. No, we didn't finish. So what does this represent? Because this is extremely important. We're going to get to this particular idea at the end of this chapter, and this is crucial. Okay. Okay. So then what does this represent?
So that's how much the cost increases for each additional yard.
When the production is 200 squared yards. Okay? So this is the rate of change, 32, of cost with respect to time, WRT, with respect to yards. That's the variable x, number of yards. When or at the production level of so that's how fast that's how fast the cost changes when we produce 200 yards. It should be squared yards, producing x. So in the formula, x is in yards. Don't ask me how they came up with it. Okay, so now C is the most important part. And you will see why. Here's the question. Compare C prime of 200. So compare C prime of 200 with the cost of manufacturing the 201st yard of fabric. So compare to the cost of producing 201st yards. Forget about C prime for a second. Let's suppose we have a production of 30 yards. And we would like to increase it to 31. I would like to see how much it costs to do that. So the difference, which is called delta C, delta cost, which is the cost of producing the 31st item, okay, which is C of 31 minus C of 30. So if we produce 30, we know our cost. If we produce 31, we know another cost. And now we know exactly how much we increase the cost. Subtracting from the cost of 31, producing 31, we subtract the cost of 30. Agreed? So coming back to our problem, how do I determine the cost for producing the 31st? It will be the cost of 201 minus, yes. What do you think? Don't answer, bless you, don't calculate anything. What do you think that cost of producing the 201st item which is the production is 200, right? So what would be the cost, you think, of producing the 201st item? Close to. It's not going to be identical, but very close to.
31.
200 plus 32.
32. 32. It has to be close to the rate of change of the cost immediately after 200. So let's calculate. So we do have, no, we don't have any of those.
It's probably going to be less though, right?
Very close. So C of 201, so this is 1200 plus 12 times 201. So this is not what I'm going to do normally. I'm going to put the function in and then determine those two values, but that's okay. So 0.1 times 201 squared plus 0.0005 times 201 cubed minus 1200 minus 12 times 200 plus 0.1 times 200 squared and minus, I have to change the signs because I'm subtracting, 200 cubed. Please check my answer.
They were talking about steam.
Say it again.
So they were talking about steam power and that's
Correct. It says compare. Where is my page? Okay. It says compare, but I haven't calculated this yet. I have to calculate the cost of 201st. I have to perform all my calculations. And then I will compare to this, which is this. But I haven't determined this part yet. Is that clear? Okay, one more time.
I got it.
To determine the 201st item, the cost of the 201st, I say this. When I manufacture 200, I get A. When I manufacture 201, I get B. How much was the increase in cost when I changed from 200 to 201 is the difference between the cost of 201 minus the cost of 200. And this is what we haven't calculated yet. So the cost of 201 minus the cost of 200, I'm waiting for someone to calculate this and give me the answer. And then we will compare it to C prime of 200, which we know is 32. But we first have to calculate this, and then we will compare. Is that better? Okay, so what did we get? I jumped. So what did we get? We're still calculating it? Well, I hope you didn't put a 1200 because it's going away. Okay.
I got 32. 205.
Very good. So I'm 32.0.
1.2005.
32.2.
0.025 dollars per yard.
0.005.
Yeah. So
32 point.
32.200.200.5.
Perfect. Awesome. So let's compare. And here's my final question for tonight. Which of these two calculations you would prefer? This one or this one? Knowing that they are so close to each other. And you don't really care for decimals. Now, if we're talking about human life, it's a different story. Or medication, right? But if we're talking about the length of a marker, I will definitely use this method to find the rate of change or the item of whatever versus doing all this. That took us 3 minutes. And this one took us 1 minute, right? Since they are so close, I prefer this. But if human life is clinical trials and something else, that's a different story. Then I may want to be super exact. Any questions? Any questions for me?